Alrighty. Hello, everyone. Good morning. It's exciting to be here today. So I just want to start by reflecting on the fact that us modern humans have really always been consumed with high-level performance. And in the world of physical fitness, we know that the pursuit of optimal performance has really been a growing global obsession. So if you look at strength, power, endurance, speed, flexibility, balance, coordination, there is specialized equipment, programs, and practitioners to optimize abilities across all these domains. But how about the brain? How about optimizing those functions that really most define us as human? Our higher cognitive abilities, our perceptions, our memories, emotional regulation, decision-making, compassion, wisdom. In that regard, I would say that we are really tragically lacking. Our traditional education system for developing minds has really largely focused on the transfer of information content and not the building of the underlying information processing systems that relies on. Our mental health care system for those with impaired minds has really had a largely siloed approach to using the blunt instruments of small molecules to repair the brain. An approach that has really generated as many side effects as effects. And I'd say that this is really just not good enough. We can do a lot better. So how about technology? What about the promise of all this new tech? It is clear that we are living in extraordinary times, right? Over the last several decades, we have witnessed an explosion in both the diversity and accessibility of information technology. And right now, we stand at the verge of a phase shift with the emergence of consumer-level virtual reality, augmented reality, motion capture, wireless physiological devices that capture all of our signals inside, and artificial intelligence. I propose that we can use this modern technology as a tool to enhance our cognition, refine our behavior, and elevate our minds. How is that possible? How can this technology have that type of impact? There's really one simple reason why. Technology can be used to create powerful experiences. And experiences are the gateway to brain plasticity, that wondrously complex dance of change that occurs in all of our brains all the time at every level, from structure of the brain, which you just heard about, to its function, to its chemistry. We know how strong the relationship is between experience and brain plasticity, right? Just witnessing a single tragic event can cause brain trauma that can impair the rest of a person's life, right? Detrimentally impacted, something we call PTSD, right? So without actually even physical trauma to the brain, we know that one single event, one experience can have that sustainable negative effect. Our challenge is, how do we use modern technology to create experiences that maximally harness this plasticity to better our lives? That is the challenge that we should face with all of this incredible innovative energy that's coming out of the tech world. How do we do that? The most effective way to do that is to create what we call closed-loop systems. What a closed loop is that you intervene in some way and quantitatively record with as low latency as possible what the impact of that intervention was. You then use that data to reformulate your intervention and apply again, cycling over and over, constantly refining. This is the most powerful way to change anything, whether it be physical or biological. In our lab, we create closed-loop systems between our brain and video games. Let me break down how this works. While you play the game, we're recording every aspect of your performance in gameplay, and we feed this information into the software. So essentially, the game is diagnosing how you're performing in real time and then uses that data to feedback an environment that's appropriate. So to scale the difficulty right to the level of your ability and also give you feedback in real time how you're doing. This drives the plasticity by creating that closed loop system. Essentially like a personal trainer being there with you every single moment, driving improvement in how your brain is performing. But we can go even further than that. we could use the new technologies of motion capture and these physiological devices to feed even more data about how you're performing into the game engine and use that as the input. And then we can use these new technologies like augmented and virtual reality to create richer environments that are more real world. So that's how we bring on some of the new technology that's emerging. Our hope is to then wrap all of this together in artificial intelligence programs that really create this multimodal integrated closed loop system. We think that this is the most powerful way to change how the brain is functioning, to rewire those circuits and lead to these meaningful and sustainable changes. So let me make this a little less abstract. Let me give you an example from our research. Actually, our first research project in this domain was started 7 years ago when I asked my lab this question: can we build a custom-designed video game with these type of closed-loop mechanics that I just described to you to enhance cognitive control abilities in older adults? Cognitive control is a set of skills that enable us to interact with our complex environment around us. It involves attention, directing your resources that are limited where your goals are, working memory, holding information in mind for short periods of time, and what we call goal management, which is essentially switching between tasks that you have parallel goals to accomplish. Our hypothesis was that we could use a game to challenge one of these domains, in this case goal management, multitasking, to see benefits in other cognitive abilities that were not directly trained but are mechanistically related, meaning that the same brain networks are involved in all of these. That was a hypothesis. So we built a game with friends of mine that worked at a video game company known as LucasArts, George Lucas's video game company, that unfortunately is no longer with us. And we built this game called NeuroRacer, and it uses exactly the closed-loop approach that I described to you to create a multitasking experience. And essentially what our participants doing are driving a car along a road which demands a lot of attention, to go left, right, up if they're going up a hill, down if they're going down, and then to respond as rapidly and accurately to the target signs, like the green circles, but not to distractor signs like green pentagons or red circles. Both of these tasks get harder as you do better, and we couple across them with a reward cycle, meaning that you only level up in the game if they both get better, pushing you to multitask, which is something that we do not normally do very well. And we showed that we could use this game as a behavioral diagnostic. So what you're looking at here is age on the axis, on the x-axis, going from 20 years old up to 80 years old. And on the y-axis, the 0%, where you see that red line, that means that you multitask perfectly. It means that you do that sign task as well when you do it alone compared to when you're driving at the same time. And if we take a look at how a 20-year-old multitasks, right, so every percentage you drop is sort of the cost of multitasking. If you ask a 20-year-old how they'll do on this, they believe they will be absolutely perfect because they are convinced they are multitasking masters, right? They practice it every moment of every day. But we know that's not true. We find that they drop almost a third in performance when they multitask on the game. Now, we already know that older adults are going to be challenged in this domain because we'd been studying it for a decade before we even did this experiment. But what was interesting is if we look in between 20 and 80 years old, and what we find is this happens. This is a lifelong change. It makes us think that aging is not about being 80 or 60. It's about not being 23 years old anymore, right? It's a lifelong process where these very, very fine-tuned, fluid abilities of the brain decline. And so we can see with a game that we can have a diagnostic tool to study how this ability changes across the lifespan. We can also use EEG recordings to look at brain electrical activity during gameplay. So that was another challenge to our game programmers, to build a game that we can actually record what's going on in the brain during play. And what we find is that this one measure, it's very important, it's a burst of activity in the theta range. It's a frequency, a low rhythm, which is coming from the front part of the brain, the part that's most involved in cognitive control. And it's engaged at the most challenging part of the game when you're driving along the road and a sign comes up. Right at that moment, you get a burst of this activity. It peaks in a third of a second, and it declines by the end of a second. And if you look at a 20-year-old, so this is looking down at a head, the average head of our 20-year-olds. The nose is pointing up, the ears are to the side. You see that yellow blob in the middle. And so the warmer colors going all the way up to red, which is the highest level of activity, and blue being the lowest, this is a third of a second later. And so you could see that this activity increases in the frontal lobes. If we take a look at a 70-year-old playing the game, this is what we see. So there's a peak there, right? It's not blue, but it's certainly not reaching the same levels. And we know this from other research that our healthy older adults, and these are healthy individuals that are tested, they have no signs of dementia or impairment, but they're still not as capable as the younger adults, and presumably not as capable as they were when they were younger adults. We see that they do not engage the prefrontal cortex, the most evolved part of our brain that's involved in this really very challenging activity as much as a younger adult. And so what we then do is bring another group of older adults, 60 to 80-year-olds, back into the lab, record their brain activity, and send them off to play this game in a closed-loop fashion at home. And they play it, I think I have a slide there of one of our participants playing at home. They play it for 12 hours over the course of a month, 1 hour a day, 3 days a week for 4 weeks. And then they come back in the lab and we see what happens. The first thing we notice that happens is that their ability to play the game and multitask improves beyond the level of 20-year-olds. And you could see that red dot right in the middle. They're activating the brain, many of them beyond 20-year-olds in the game, and not just more robust, but more rapidly. This is a very clear example of neuroplasticity at the functional level occurring in older adults in response to 12 hours, which is not really all that much when you think about the lifetime that occurred before they played this. We also know that if we look at them 6 months later and play the game, we see that there's a non-significant decline in their ability to multitask in the game. Perhaps what was most exciting is that we find that those other skills we were interested in, working memory and attention, also improve significantly, even though it was not directly trained by the game. This is this elusive transfer that we're always looking for. And it's not a magic trick. It happened here because these skills, these abilities are mechanistically related to one another. We had two control groups. One group played no game, and the other group played that same game, but in single tasking version. So they did the sign test, they did the driving test, but they never did them at the same time. They did not show any improvements in brain activity, and they did not show any improvements in these skills, this transfer skills. So it's not just that anything you do for your brain is good for you, just like not anything you eat or any drug you take is going to be equally impactful. It was the challenge in this multitasking domain that led to the transfer in this case. We were really delighted that this was published after 6 years from the beginning of building the game to the study in Nature at the end of 2013. You could see Nature gave us a very complimentary title of the Journal of Game Changer, which has sort of tortured me ever since. And it really led me to message that as excited as I am about this particular game, what I hope the game changer is that we learn that we could work very carefully with professionals in the industry that know how to build this type of technology, and then create it and target it to known deficits in a population, and then do a carefully controlled placebo study and show that you have impact and use neural measures to understand what the mechanisms are so that you can iterate and keep developing. This is the approach that we have to take if we're going to really change how we approach improving cognition across those that are healthy and those that are impaired. Just a small note, we have a whole initiative to move this into the real world. I helped co-found the company called Achille, who is here over these next couple days, and filed the patent behind the technology you just saw. Achille has now done an amazing job of making that game so much better as a game, more fun by using art and story and music, which are essential if you don't have violence in your game and you want young people to play them. But also refining those closed-loop algorithms to make them more effective, more rapid. This game is now going through multiple clinical trials and is just about to enter a study for ADHD to try to seek FDA approval. So the pilot data look very convincing. There's also studies on depression, post-traumatic stress disorder, traumatic brain injury, and Alzheimer's disease all beginning. So that game is not available in the iTunes store, much to a lot of people's dismay, as my email informs me all the time. But the idea is to really transform this field by putting it at a level that physicians, who are incredibly conservative in this domain, not all of them, but some of them, that they would feel confident that this is another therapeutic tool. This is a digital medicine that they should just as easily reach for as reaching for a pill. Right? So hopefully we'll see prescribable video game for ADHD from that type of research very soon. So now I want to tell you about what we're doing in the lab. So that's an example of something that has left the lab. We have a new lab called the Neuroscape Lab that I built last year that's really designed to bridge tech and neuroscience in a powerful way. I just want to give you a quick look at what it looks like. So this is our lab at UCSF. This is our new neuroscience building. And below you could see our lab. It doesn't look like a neuroscience lab, but I assure you it is. That's the control room on your left that's sitting on the opposite side of the room as our experimental room. So there are people come in, they play new games that we're developing, and I'll tell you about a couple of those, to try to enhance their cognitive abilities. These involve all sorts of new technology like motion capture, virtual reality. I'm going to give you a little bit of taste of that. But the idea here is that as we develop new tools along the lines that I just described to you, we could record everything possible. Eye movements, body movements, physiological responses, emotional responses, performance, brain activity while people play, so that we can understand the ingredients, the active ingredients of our technology that leads to meaningful change. We have another technology, we call it ACE, Adaptive Cognitive Evaluation. And what ACE is an approach to use technology, apps, to understand how people's cognitive abilities are functioning, and to do it very rapidly. So we use the same type of adaptive closed-loop algorithms that we use for our games, but here we just use it for assessment purposes. So let me tell you a little about new games. So we'll just step through them really quickly since we don't have a lot of time, but I'm happy to tell any of you about more of them after. Here's 4 games that we've been working on. Metatrain, Rhythmicity, Virtual Attention, Body Brain Trainer. So we've been working on these games for the last 2 to 3 years across most of them. And just to tell you a little bit about them, Metatrain is a game that takes the principles of concentrative meditation, and then we integrate it with the game mechanics I described to you of adaptivity and feedback. So it's an iPad game that's meant to help improve internal regulation, self-regulation of internal distraction. Rhythmicity is a game that has been stimulated and inspired a lot by a colleague of mine, Hart, who's the drummer from the Grateful Dead, and who's very interested in this domain of rhythm as a tool not just of entertainment, but actual impact in improving how our brains function. And the idea is that our brains are rhythmic and also rely on exquisite timing. And so Rhythmicity is a game to teach you to become more rhythmic, again, using the same type of skill, same type of mechanics of adaptivity, with the hypothesis that if you become more rhythmic, the rhythms of your brain will be refined and you will see improvements in your cognitive abilities. Virtual Attention is our first foray into the world of virtual reality. The goal is to not just to teach you how to focus your attention, but to actually expand and broaden your attention. The very skill you need, for example, when driving, where you need to focus on the road, but also sensitivity to what's going on the sides. I think it's a perfect use of virtual reality, taking advantage of the fact that it has a very wide field of view and depth, something that you just can't do with a monitor. And then Body Brain Trainer is maybe one of our most exciting games right now. It is a game that integrates physical training and cognitive training in one game experience. So while the game is adaptive, so while you're doing all these cognitive challenges, and as I described to you, the game is getting more difficult as you get better, as your attention gets better, as your memory gets better. We're also recording your heart rate and feeding that measure into the gameplay. So we could hold your heart rate right at a level based on a VO2 max that we do beforehand to challenge you both physically and cognitively right at the level where you are most susceptible to change, where you're most induced. It also happens to be the place that's most fun to play. It's not so hard that it's frustrating, not so easy that it's boring. So that's a little bit of an example of those games. All of them are now in research studies. Rhythmicity will start in a month, but the others are all several months in already. And our goal is to now bring the highest level of scientific methodology to figure out how these work. So we do everything from MRI, structural and functional, EEG, stress monitoring, blood work to look at inflammatory markers. We do sleep monitoring at home using devices. All before and after, many things actually during 6 weeks to 2 months of training. Right now, they're all in younger adults, but we'll move it into younger kids, children, and older adults in our next move, and then out to clinical populations. But the real win will not happen this year or next year. It's what I call Neuro CrossFit training. It's how all of these games actually work together, right? We don't want to repeat some of the mistakes of our past and work in silos, that one game is just going to be the holy grail. They're all going to supply different aspects that improve our function, and that's what I'm excited about. While that's going on, and it's going to take us a while to look at how they interact, I have actually been training on these games myself. 3 of them, Metatrain, Rhythmicity, and Body Brain Train. I spent 2 months playing and recording data before and after. I'm not going to share that with you now, but I can tell you it looked pretty good. We're still waiting on some of the blood data, but I don't know what the outcome's going to be, but I can tell you I have great enthusiasm of what we're going to see over the years as I continue to train. So let me conclude now with the most science fiction sounding part of it, but I assure you that we have a lot of research efforts in our lab into the idea that video games work because they selectively activate neural networks, something that we've never successfully done with a small molecule. So they activate the brain, and then by using a closed-loop system, we put pressure on it and change it. But we think that's just the beginning. We could then bring on other approaches, neuromodulation and a new view of neurofeedback, to really enhance those effects. To do that, we created and we're still working on a new technology that we call the glass brain. I don't have that much time to talk about it. If you Google it, you'll read tons about it. But essentially, it's a combination of MRI and EEG that allows us to visualize ongoing brain activity in real time. You're looking here at different frequencies in the brain that are correlated with a video game that's being played during this recording, as well as these flows of how areas are communicating with each other. We bring all of this data into our game engine, and it gives us this amazing ability to just navigate a human brain with a joystick while someone is functioning and someone is playing. We see that it has great diagnostic potential to see what's occurring in someone's brain while we challenge them in a specific way. But what's most exciting, and I'll conclude with this, is that this can be a gateway to another level of closed-loop systems. So let me just wrap it all up in one slide. 2015, you go to your doctor and you have problems with your attention. Let's say whether you're 12 or 80, this is largely the approach, right? We get a pill that has the problem in that it's blunt. As I said before, it activates the brain. It acts on a neurotransmitter system, but it doesn't act on a neural network. And this is why we get side effects, because we have to push the doses too high to get the effects we want. We're hoping that in 2020 we could decrease the doses and then use something like ACE to get an assessment to know where we want to target our intervention, right? So it's targeted. Then use a video game to activate a specific neural network with the closed-loop dynamics to put pressure on the system. Then using the glass brain, we could take EEG data and feed it into the game. So the game is essentially diagnosing what's weak about how your brain is processing information, and then using that data to guide the adaptivity and the feedback. So it's like a surgical approach. We think of it as like a gamma knife that we could focus our engine right on those processes that are most efficient. We can also take EEG data and feed it into a stimulation device to stimulate the brain either with direct current or alternating current, which now research from our labs and many others are showing is another way of enhancing plasticity. You can imagine you have a traumatic brain injury, that this approach, being able to focus on the neural circuits that are most vulnerable, most affected, as well as increasing plasticity with stimulating right at that right frequency, could have a really profound effect on improving those abilities. And so what we wind up with here is something that's targeted, personalized, not just to the individual, but to how that individual changes over time. Multimodal, right? This is not a siloed approach. All these things can work together, including with molecules, with pharmaceuticals, but probably at much lower dose, maybe 1/10 of what we use now. And it's a closed loop, multiple closed loop systems interacting. And the beautiful thing about this technology is that it goes in the real world in real time. It's nothing that has to take place at visits that are separated by months, right? It's something that you could do at home and bring into your life to keep refining these abilities. So over the next 10 years, and this has already started, this is not a wish list, all of these collaborations are in process, we will see how this technology could have an impact on the brains of people that are suffering from all of these different conditions, as well as how this can act as a tool to improve the brain of people who are not suffering as an educational or as a wellness approach where it'll impact everyone's lives. And with that, I'd like to thank you for your attention. So we have some time for questions.
Come to the mic if you've got a question.
You mentioned your work with attention deficit hyperactivity disorder. Are you doing any pilot testing of that? Do you need candidates or people that can test it?
So what has occurred with ADD or ADHD, depending on how we recruit for that, is that Achille has really taken that on as their first main target. So they have completed a study. I'm an advisor now, which is sort of nice to step back and let my colleagues figure out the next part of that story. And so their game is called EVO, Achilles game, and that game has finished a pretty large pilot study on ADHD that was led by a principal investigator, Scott Collins, out of Duke, and the data was very exciting. They actually just announced at a conference last week. If you go online, you could read about it. The data looks really nice, and that data was presented to the FDA, who was very enthusiastic about it, and that is beginning a full-out, I think, 5-center clinical trial to prove the game as a therapeutic device for ADHD treatment. There are other ADHD studies going on, more mechanistically, not for approval at UCSF. And ADHD, as I know everyone here appreciates, is a very, very complicated diagnosis. It's constantly changing. What does it mean if you're 60 and you have attention problems, which is one of the main areas that we study? There's almost, that diagnostic entity doesn't even really exist in that age group, but yet in our clinical experience, we know it's true. So I think that we're going to be seeing a big expansion of how a tool like this can impact people that have attention deficits across the lifespan. I think that this will really help expand our view of what we can do to people independent of what age they are.
I wonder if you could say any careers that you would recommend to someone who wants to work in this business that you've got going. Where is the future for the students and the people who might want to change careers to get their foot in the door of this kind of work?
Well, that's an easy one because it's so vast. It's such a multidisciplinary field. We have people that come into our lab. Some of them are programmers. They're from the tech world. They're game programmers. They're signal processing engineers, or they're psychiatrists or psychologists or neuroscientists or bioengineers. We see an incredible diversity of people that have something to contribute to this. So, those are the general types of backgrounds that I see most frequently, and we have them all as part of our team because they all play a different role.
It's a great presentation, and
Thank
I'm
you.
a big Mickey Hart fan, so.
Thanks. I had some Mickey Hart videos I was going to show, but I didn't know how pressed I'd be on time. We have this one video. Mickey and I did a talk for around 3,000 people in California, and we put a virtual reality headset on Mickey, known as the Oculus Rift, which is Facebook's headset now. And we created a virtual reality drumming game, a sort of predecessor of Rhythmicity. And so Mickey in all his glory is drumming on stage, giant 120-foot screen, 30 feet high, so you could see his world. We could put all this Grateful Dead sort of call-outs in there. And then next to him, so Mickey's not just wearing a virtual reality headset, he's wearing a 64-electrode wireless EEG set that we built specifically for this. Next to him is Tim Mullins, who's one of our head engineers on this project, on the Glass Brain project, and he's wearing a virtual reality headset. And what you see over his head is a view of Mickey's brain firing in the Glass Brain in real time. So it's sort of like a neuro-nested dolls, like Tim's in Mickey's brain, Mickey's in virtual reality, and it's pretty epic. It's online if you want to see it.
I have a question and a concern.
Okay.
The question is, have you looked at the effects of these technologies on hemispheric lateralization? Is there differences between activation and plasticity in the left hemisphere versus the right hemisphere? And
yeah, so all of our data on the plasticity effects have been with EEG so far, and those effects are pretty midline. We are now, all of the studies I showed you, BBT, Body Brain Trainer, and MetaTrain, now have all functional and structural MRI data, and we have like 3 more weeks of data collection. We're 6 months into it. So I don't know about laterality, but I'm sure they'll be part of papers that you'll see pretty soon.
And my concern is that there's a notion that data in is what data comes out, and when you talk about a closed loop system, the brain is not a closed loop system. It's an open system, and when we begin sort of confining our technologies to a closed loop system, there's all sorts of concerns about where that leads us.
Well, I mean, there's always concerns with new technology, starting with like pen and paper. I think that the list is long of things that you have to take into consideration when you do create a closed loop between the brain and a processor and a computer, because I think it will have potent effects on rewiring those circuits. So it's something that we take very seriously. We have full lab meetings about how do you monitor for potential side effects or changes in cognitive systems that may be at odds with what you're trying to improve. So I agree with you. I think that the responsible approach is not to think, oh, this is a video game, it's trivial, but to take it seriously and say, if we're going to consider this a type of medication, a type of medicine, a type of education, we have to be responsible about what effects might be occurring that we're not looking for. So I think your comments well taken.
Thank you. Thanks.
Hi, thank you for coming. I wish I'd found you about 2 years ago. I have a son who has severe depression, has been hospitalized about 3 times. And 2 years ago, I found the Oculus Rift was going to be coming out. So I asked him if he could think of a virtual reality situation that would be healing. He spends a lot of time on the computer. And he's still working on that. But my question is similar to the first gentleman, and that is there a way for somebody to get into these studies or to be part of this now?
Well, so as a researcher, as a participant?
As a participant.
Yeah, so research participants in our study are pretty much people that live in the Bay Area right now.
We'll move.
Okay. Well, then we'd love to have you. And that's only because we tend to do this, like what we call the deep dive, right? MRIs, EEGs, like you got to be local. But we're working closely actually with Apple and other groups to start doing mobile studies. So our real goal is to do studies on 1 million people. There are questions that you can't answer in a laboratory with 20 people, like real life transfer and finding those rare cases of people that have adverse reactions. You need numbers. And we can't do that given our current system. We do something valuable. We understand what's going on in the brain, but we want to do that in parallel. So once we start doing mobile studies, and you will definitely hear about it, we will be recruiting globally. We definitely want this to be a global mission.
Hi, I was wondering if there's any interest in focusing these strategies on addiction.
Yep, there is interest. So again, what has happened is that we build these tools and we validate them as carefully as we can on people that are generally healthy. That's the most responsible way to start and the most accessible population. And then we start moving into different age ranges. And what we have found is that people reach out to us with clinical populations that they find interest. That's always the best way. So we never really seek it out, else you're constantly pushing. We're more like someone will approach us and say, I think that this would be perfect for my autism population, and this is why, and then we'll collaborate. And we have had lots of interest recently for addiction as well. And we haven't started that, but there's a lot of great addiction researchers at UCSF that find it interesting. And this is just so fascinating to think that something like a video game where there's concerns of attention problems and addiction being used to treat both of those things. So I love that, flipping it around, and it's all possible. I mean, it takes thoughtfulness on how to do it and care and responsible monitoring of effects, but I do think addiction is possible as well.
I have a question about the methods that you're using to assess the communication in the brain circuits.
Yeah.
It sounds like you're using QEEG and you're using imaging. I'm curious in your assessment of the coherence,
Yeah.
Are you using dyadic measures or multivariate measures?
We do multivariate Granger causality in the glass brain, but we do a lot. There's like 6 faculty and everyone has their own favorite tool, but we do a lot of multivariate measures.
Yeah, I have a question over here.
Oh, okay.
Hey.
Hi.
I'm curious if you're monitoring any of the dietary data of the individual that you're investigating, so that if they're at an impaired state when they start the training, could you potentially be actually increasing neuroinflammation by activating a brain that's pretty deficient in nutrients?
Yeah, we try to monitor as many things as possible. The list gets pretty long. Sleep and stress and physical activity and work activity and nutrition. all of which is incredibly important. So we do collect a lot of data. The problem is, and this is just being totally transparent, is that when you collect that much data and you don't have specific hypotheses for all of them, they become statistically impossible to manage. But we do it anyway, and if we see something come up again and again, and we have seen some things, we're like, oh, there's something going on there, and then we'll use that to guide a hypothesis, and then we have the statistical power behind it. So we do collect that data.
Thank you. As a mental health clinician working with adolescents, I'm wondering if you could comment on the benefits or challenges of games such as Grand Theft Auto, or if you could recommend any video games that are out there now that may be a benefit.
Yeah, I get that question a lot. My other question I get a lot is, what games do I play? Yeah, so, I will tell you that there is data, and some of that data actually inspired me to work on video games almost 7 years ago, showing that consumer games that are not directed at cognitive health has shown benefits on cognitive performance. Those games usually fall in the category of first-person shooters, action video games, if you're familiar with them. Grand Theft Auto is not exactly in that category, but those games, like Call of Duty, have been shown to improve cognitive control abilities, those very abilities that I told you about in older adults, in the young people that play them. Probably not so surprising if you play these games. They're really taxing cognitive control. They're very, there's lots of interference, there's careful, selective decisions, there's the need for working memory and shifting. They don't use adaptive algorithms in the way that we do, so I don't think they'll be as effective. So I don't know about Grand Theft Auto in particular, but I could tell you that some consumer games do have benefits, and that's been shown mostly for first-person shooters in the cognitive control domain. But I do want to make very clear, video games are like saying food or drugs. It is a vast category with many, many different types of games that have different active ingredients that might have different positive and or negative outcomes. So these very rapid games work on cognitive control, but other games might have abilities, benefits on different things like spatial attention. There's lots of interest in Minecraft, which is more of a sandbox game where you seek things out, the goals are not as defined. So Minecraft is one that comes to mind. My favorite game is a game called Portal 2 by a company called Valve. It's a spatial game, and I think it's awesome.
Just a real quick question: as this becomes part of like the therapeutic field, do you have an idea about how insurance companies are going to feel about this treatment option? Will it be covered? The affordability of iPads for some of the populations and things like that?
It's an open-ended question. We talk about it, but our first step was to get approval. But I think that even some conversation I've had here, even just as far as yesterday, are opening up some interesting opportunities. There's other big questions like adoption, like even FDA approval, even reimbursement. It's like a paradigm shift for a physician to pull out their prescription pad and not write a drug, but write iPad for a month. Right. But it opens incredible opportunities beyond the ones that we even talked about. The fact that they can get data every single day in a person's home, I mean, that's an access that we never have had with a molecule before. So there's still open-ended questions, that being one of them. Last one? Last one.
I'm in the neurofeedback world, and we're involved in a large-scale TBI study, and we just had a horrible problem with the placebo control as the gold standard. So how do you handle that with something interactive that's not just a sugar pill or a medication?
It's a great question. We've spent almost a year trying to figure out how to do double-blinded, placebo-controlled studies using a video game. We feel like we have that worked out now. Even our Nature paper was not perfect in the methodology. It was probably one of the best up to that point, but we want to go to the, we look at all of our critics out there, there's not a ton, but everyone has critics, and say, what is valid, what is not valid about what we're hearing from you, and the idea of the placebo can be improved. So very, very briefly, how we do our placebo is that we have one game that we think has this active ingredients. We have another game that we think has no active ingredients, at least that's what we believe, sort of like a sugar pill doesn't have active ingredients. We then go and do an entire study where we take people and say, you're going to play this game for a month, and we're going to test this, and this. And we show them what we're going to test, and we ask them to rate how much they think this game is going to improve these abilities. Then we have another group of people, and we show them this placebo game, the game that we don't think is going to have any action, and we ask them to do the same rating. When we find that there's no statistical significant difference between those groups, in other words, expectation is the same, as long as they don't know which group they're in, we believe it's a placebo control. Placebo is really about expectation. If they have equal expectations that that game is going to have the same impacts, when you see a difference, it's not caused by expectation, and it's not a placebo effect. That's how we do it. Okay, thank you, everyone.